that's something entirely new. All right. Uh, some new topic. I think I mentioned that our midterm will only be on the first three topics. The midterm will cover what's the name? The conjugate beam method, the moment area method, and then the three moment equation method. Okay. So let's look at some other method that we can use in what's the name? In calculating deflections, okay, in beams. So we have this method called the energy methods or deflections. Deflections, yeah. So that's the spelling using energy methods. So the if you look at the moments area method, and also you look at the what was the name? We look at the conjugate beam method. All right. So we usually had these geometric methods. Sorry. So I think we had the moment area, and also we had the conjugate beam. All right. So these were the methods that we looked at, right, to calculate slopes and also calculate deflections. But one of the key things about these two methods were that they were used for very simple loads, okay, or simple loadings, okay. So nothing too complicated. The loads were fairly straightforward, and we could use that to analyze and they were also mostly for beams, okay. We didn't really do anything outside of beams, okay. But then we know that there are structures around us which are not simply beams, but we could also have, or we can have frames. We can also have trusses, okay. So an example of a frame, so this could be a frame. Okay. So maybe it has some loading on it. So this could be a frame. So let me put here frame. And then in your basic structures class, I'm pretty sure you learned about trusses. So again, an example of a truss. Let me do it this way. Yeah. So this could be a truss. All right. So we can find deflections of frames. We can also find deflections of trusses. Okay. The two geometric methods or approaches will not be adequate, or would these types of structural systems will require or their calculations are a bit more complex, and as such, the geometric methods will not be adequate or will not be enough in trying to solve or compute for the deflections at various points. All right. So we want to formulate another method, which we call deflections using the energy methods to calculate the deflections of various sections. All right. So before we formulate some of these equations, let's look at a few things, a few terminologies, and then understand what we mean by the energy methods. Okay. So let's look at what we call external work, and then internal work. Okay. This internal work is called strain energy. So again, like I said, for more complicated loadings or for structures which have frames and then trusses, we we can use the energy methods equation or the energy methods for the computations, all right? And the energy method is primarily based on the conservation of energy, based on the conservation of energy principle. Okay. I think that says that energy is neither created nor destroyed, right? But it transforms from one state to the other. Okay. So so this principle in another form can also be written as the fact that so let's say this states that all work done by external forces acting on a structure, on a structure is transformed into internal work. Okay. Into internal work or into strain energy. So simply put, if UE is external work, then UI, so the U stands for work done or energy, all right? So this is external work done. And then here is internal work done. Okay. So we are saying that if you have a structure and there are external loads on the structure, what happens is that these external loads can be transformed into the internal behavior of that structure. All right. And we can relate the two, okay, without using the principle of the conservation of energy. So that's the idea with which we are working with. So we can formulate a set of equations. But even before we formulate the equations, this is usually true if you're looking at the elastic region. Okay, typically the elastic region. And the elastic region is a region whereby when you apply some load to a structure, and then there's some deformation. So let's say you have a beam, you apply a load P to this beam. Okay. At some point, the beam will deflect delta. Okay. If we take the load away, okay, so we take this load away, we are assuming that the beam would return to its original position, all right, or its undeformed position. So once that happens, that means that we are within the elastic region, okay, or within, we've not exceeded the elastic limits. So based on that, we can look at let's say if we take, for example, the external work, we can look at the external work done by external forces and also done by moments, or some will say couples. Okay. So the external work is simply the work done by external loads, and these loads can be forces, and they can be moments. Okay. So let's look at the work done by, let's say, an axial force or an axial load. Okay. So let me call this 1 and then call this one A. Okay, so this is the axial load, just to explain so that at least we follow what is happening. So let's say I have a beam, okay, or a bar. This is my bar. So this is its original length, L. And let's say apply a load P at this end to the bar. Okay. So as I apply this load, let me just draw a plot of force times x, or deformation. Okay. So when I apply this load, initially when P is 0, or when F is, let's say when F is 0, there's no deformation, there's no elongation of the bar. But as I gradually increase P from 0, or as I gradually increase the load F from 0 to P, there will also be a gradual increase in the deformation. So with time, this becomes my deformation at P. So based off of that, I can have a triangular representation where this is P, and then here I have delta. So this section right here, the area under this curve will be the external work done due to the axial load applied to P. Okay.
Hello, sir.
Yeah, hello.
Yes, so, I'm sorry, I lost track of time during the break. The topic we're dealing with now, please, what's the topic?
Um, deflections using energy methods. Sorry.
All right, so thank you very much.
You're welcome. So here we can see that P would gradually, or the force F will gradually increase from 0 all the way towards P. Okay. So that the work done by P in this case, so the work done, which is the external work done due to this axial load, will then be the force applied um, times the distance moved. Okay, so that's the general equation. All right. So it's again the area under this curve. So in that case, the UE, or the external work done, will be half of P delta. Okay, so that'll be the area of this triangle right here. For now, we are just trying to understand what it means to have external work done. All right, we'll see how we can incorporate these later on in analyzing problems. Okay. Now let's look at another, again, still under the axial loads, where I'm assuming you guys are doing strength of materials, right? So yeah, you've passed through some part of your work which you were looking at strain energy. Am I right? Can someone answer me?
Yes, sir.
Okay, great. All right. So these things shouldn't be new to you guys, I'm guessing. Okay. So there's also another case whereby so I'm looking at this, just redrawing everything. Okay. So this is my delta. So let me just redraw everything here. Okay, yes, fine. So this whole space here. So this is so here's P, this whole thing is delta. Great. But let's say we apply the load P to the section. All right. Which went so it has undergone some deformation. All right. Then after this deformation, we apply another load to the system. Okay. So here P is already applied. Let me just create enough space. So P is already applied. Then we apply another load. Let's call it F prime to the system. In addition to the already applied P, which means that our beam would undergo some extra deformation. Okay. So let's call this deformation delta prime. Okay. So it means that on top of P, so this is where P ends, we have another load applied right here up to F prime. So we can also have this set of loading where the distance here is delta prime. Okay. So now if I want to look at it, the work done by both P and F prime, then I'm looking at this entire section right here. So this is the entire work done by both P and then F prime. So let's say work, let's say total work done will be equal to, which is UE. In this case, will be equal to, let me just put the UE here, right here. Will be equal to half of F prime plus P. Let me do it this way. Yeah. Delta plus delta prime. Okay. So let me just so P plus F prime. Okay. So the first deformation is due to P. All right. Then the second deformation that we have, or the extra deformation that we have, will be due to the F prime. Okay. Let me just name these points. A, this is B, C, D, E, and then G, because I have F somewhere already, so I don't need to. So this is X, it is the total load F, all right, or the load F. Okay. Now take this, we know that work done by P only, work done by P only will be equal to half PA, or half P delta, which is the same as this region ABG. Okay. The same as the region ABG. Then work done by F prime only will be equal to half F prime times delta prime, which is the area BCD. Okay. Then work done by both P and then F prime will be equal to the entire area over here, which is what we had. So it'll be equal to the entire area ACE. The entire area right here will be ACE. But there's also a third part, work done by P when the additional load F was added, okay, or was applied, when additional load F prime was applied, will be this region right here. Oops. To be this, let me just go back. To be this region right here. So this region here is as a result of the extra or the additional load that was applied. So the F prime that was applied will cause another work done to be done by P. All right. And this will be a rectangular, what's the name? Rectangular work done. And it will simply be P times delta prime. And that will be equal to the region B, D, E, G. Okay. If F was not applied, then this component goes to 0. Okay. If there was no F prime applied, then this side goes to 0. But because of the presence of F prime, we have work done by P. Okay, so an additional work done by P. Okay. Again, most of these will not make too much sense to us for now, or even if they do, which I think they should to a larger extent, we don't really know what we'll use them for now. But as time goes on, we'll get to see how these things work. Okay. So here, let's say UE prime then becomes P delta prime. Okay, so this is what's the name? So this again is the work done by P when the bar undergoes further deflection delta prime. Okay. So in effect, this is the work done by um, axial forces. In the when you were looking at the I'm just sidetracking. When you were looking at basic structures, and I think your focus was on the trusses. One thing you learned about trusses is that they are axial members. All right, they don't they have no resistance with respect to shear and bending. So they only the individual members in the truss transfer loads or transmit loads through axial action. Okay. So that's the reason why we are starting with the axial forces, because we need these informations along the line to formulate equations for axial behavior of trusses. Okay. So now let's look at the second B, where we have moments. Okay. So if we have moments, what would that be? Okay. So again here, the for moments or couple of moments or moment couple, depends on how you want to look at it. The external work done will be equal to the moments applied times the angle through which the moment rotates. So let's say we have this bar. And so here we're using bars to explain. Then we apply moments to it. Okay. It means that this bar would rotate around the support. So we'll end up with another. So this would be the rotation. So the angle of rotation here is theta. Okay. And again, if we were to apply, if we were to apply these moments, so let me have the moments here. if I have to apply this moment from 0 and then increase it to a certain value, the same way the rotation would also did I leave something out? Okay, I left something. Let me just move this down here. I'll come back to the moment. I think I left something important out. Let me just shift this whole thing down and create space for it. Okay, good. I need to write one more equation, which I almost forgot for the axial. Let me just put over here. So let's generalize the behavior of axial forces. So if let's say we have again looking at the bar, let's take a small element of the bar. Let's call this small element dx. Okay. Then let's apply some force, which is a function of x. All right. So this particular system, it means that the change in external forces or the change in the external work applied will be equal to the force applied times the x. Okay. Whereby the total work done will be equal to integrating the force applied dx. Okay. So most of the equations I wrote up here in terms of this, in terms of even this one here, in terms of that, I mean, all the questions I wrote up here, this is the general formulation of the equation for the axial forces. All right. So we can have limits. In this case, if I'm to look at it, so my limits can be, if I'm to use this approach, then my limits can be from 0 to delta, and then I can have that or some other different limits. But generally, this is the equation for um, deflection. I mean, or for work done when we are looking at external loads in the axial directions. Okay. So here I can easily draw a plot to indicate what this means. So this could have, let's say, a parabolic shape, because I don't really know what shape it could be. So it could be any shape. And then this right here is this equation, because we don't really know what shape that will be. So it becomes a generalized equation. It will suit whichever mode we are looking for. Okay. Because once we're able to write an equation for F, and we know our limit of integration, we can then find the external work done due to the axial forces. All right. So back to our moment. So here I was saying that with the moment, we can also increase the moment from 0 gradually to let me change the color of this to some to some appreciable value. So again, you see that as the moment is increasing, you also have uh, your rotation or the theta value also increase. So we'll end up with something very similar to the case of the axial load, okay, whereby the external work done due to this case here will become half m theta. Okay. In the same vein, after we have applied the moment m, and then we apply an additional moment, let's say m prime, we would end up with something very similar. So let's say adding an additional moment m prime, then it means that our plots will change slightly. Let me do it this way. Do it this way. Okay. So this becomes, so this is where you have your M prime. This is where you have your M. That the rotation here will be theta, and then for the second part will be theta prime. Okay. So again, very similar to what we had in the case of the in the case of the axial forces. So we can see that the extra work done by the moment M will be equal to the moment N times theta prime. Okay, and then the work done by M prime will be equal to M prime times theta prime. Okay, then the total work done, let's say UET will be equal to, sorry, this is half, half M prime. It becomes half M plus M prime times theta plus theta prime. Okay, so it's pretty much very similar to what we had for the uh, for when we have these external loads. Okay, so these are the external work done when we have external loading. So if we have moments and also have what's the name, axial forces acting on the structure, these are the external behavior or the external work done. Now let's look at the internal work done. So let me see. Internal work done. So that'll be the strain energy. The reason why we are calling this strain energy is because there's the energy required to cause some strains. Strain is simply deformation. All right. So it's just a type of work done which leads to the deformation of the structure. And that's how come we call it strain energy. So in other cases, it could be a different type of energy. But for the purposes of deflections, the internal work done is due to strain energy. All right. So again, let's come back to our bar. Now we are looking at axial forces again. So for strain energy, let's look at bar. So here I'm going to change P into N just for illustrative purposes. So P is now N is the same thing. Okay. So you have these behavior. All right. We want to convert these external forces which are acting on the beam into the internal behavior. So the internal behavior is to look at the stresses and strains in the bar. Okay. We know that we've learned that the axial stress sigma is equal to the axial force divided by the cross-sectional area. Okay. And then we also know that the Young's modulus E is equal to the axial stress over the axial strain. E is equal to axial stress over the axial strain. And if this is the length L, then the axial strain epsilon. So the stress is called sigma, axial stress is called sigma, axial strain is called epsilon. All right. So this is equal to delta, delta over L. All right. So we want to formulate a set of equations which would then give us the internal, because the stresses and strains are the internal response of the beam to external forces. Okay. So let's see how we can achieve this. All right. So sigma is equal to n over A. So here n is the same as P, or I'm just trying to change so that we follow a certain pattern. Or let me just do it this way. N over A is equal to E epsilon. Oh, yes. So sigma is the same as the Young's modulus epsilon. All right. So and then epsilon is also the same as delta over L. So this one becomes E into brackets delta over L. Okay. So this implies that N over A is equal to E delta over L. So if we make delta the subject over here, then delta then becomes NL over AE. We know that the external work done should be equal to the internal work done. Okay, so in this case, our external work done, UE or U sub E, be equal to half N delta. Okay. So wherever I see delta, I can put NL over AE. Okay. So this will mean that my internal work done, U sub I, will be equal to half N into brackets NL over AE. So this will give me N squared L over 2AE. Okay. N is the same as P in the previous computations. Okay. So it's not anything there. So then this becomes the strain energy in the bar. Again, we'll come back and look at how to use these equations to help us to solve some problems. Then let's look at the strain energy due to bending. Okay, when there's some bending action. So if you have your beam, let's say a beam like this, and then we apply some load to the beam. Definitely this beam would undergo bending. Okay, so the beam would deflect. So this would be the deflected shape of the beam. Okay, so there's some bending going on. Okay. So let's say we take a small portion of it just to analyze this portion. Let me change the color of the load. All right. Whatever load, it might be P, might be whatever load. Okay. It could even be a bending load also. So it can be any load. So if I take this small section dx and I expand it a little bit, oops. So then this becomes so this is how that small section dx would expand. Okay. So because I'm cutting that one out, you have these internal moments. Typically to be axial shear and bending moment, but we are focusing on the moment. So this moment M, moment M. So as we apply the moment to the X, we would realize that there'll be a change. let me just show. This becomes a neutral axis. So you see that if you compare to the center and you draw a tangent, you see that there's a change d theta. Okay. And then from our days in the moment area method, we know that d theta is equal to m over ei dx. What's wrong with my handwriting? M over ei dx. Okay. At least we have already established that from previous computations. We also um, okay, so you also have from the external work done as what half m theta. Okay, so if we are to differentiate both sides, then we have what um, du du sub e being equal to half of m d theta. All right, so we can sub this into this equation right here, and then we'll end up with, so then by introducing the internal behavior into this, then we can calculate for the strain energy due to bending. So in effect, we can also have du sub I being equal to half m d theta, and then this becomes half m to bracket m over ei dx. All right. So dui becomes m squared over 2ei dx. So if we were to integrate it, then it means that our ui, which is the strain energy due to bending, becomes we can integrate from, let's say, 0 to x, m squared over 2ei dx. Okay. So this becomes the strain energy for bending. Okay. So strain energy in the beam due to bending. Right. So we have established a few things which we are yet to fully use them to appreciate what is happening. Okay. So this is these are equations based on, at least we are looking at just what external work and then internal work is, and we have been able to derive 4 different equations or 4 sets of equations, 2 for external work done and then 2 for internal work done, and then under each we are looking at both axial and then bending. Okay. So once we are able to formulate these equations, we can use them to calculate deflections. Okay. So this is based on the principle of working energy, or the conservation of what's the name? Energy. All right. So let's say I have this beam and I have a load P acting on the beam. This becomes the deflected shape of the beam. So this is delta. And we know that so this is A and B. So let me call this delta B. Okay. We know that delta B from conjugate beam method or moment area method is PL cube over 3EI. I think so. Right. So we know this already. Let's just see if what we'll be doing will be something similar to that. So anytime you have this particular case for the external work done due to P is simply half P delta. All right, so the same delta. Let me just make it delta so that I don't have to be writing sub B. All right. But this load with respect to the internal work done will be equal to, or this load is going to cause a bending behavior. So in terms of the internal work done, it becomes theta, if this whole thing is L, if here's L, then it becomes the integral of m squared 2EI dx. Okay. So the external work done should be equal to the internal work done. At least that much we have already established because of the conservation of energy. All right. So let's find, we already know what the external work done is, half P delta, but we need to find the internal work done or the strain energy. All right. So we need to formulate an equation for the moment M. Okay. So if I take my diagram again, and I have P here, and this is P, and then this is X, then it means that, let me just change the color of X to red. So if this is X or X is going towards the left, then it means that my moment M becomes minus P times X. So the moment equation for any point on the cantilever from the right towards the left is minus Px. Okay. So based off of that, I can write that my internal work done, Ui, from 0 to L, is simply minus Px all squared over 2EI dx. So if I integrate, I get P squared over 2EI x cubed over 3 with the limits of integration being 0 and then L. Okay. So this will give me P squared L cube over 6EI. So now I have my internal work done and I have my external work done. So it means that um, since U sub E is the same as U sub I, then it means that half P delta will be equal to P squared L cube over 6EI. So we want to find delta, so we can make P the subject. We can make the delta the subject. So here delta becomes P squared L cube over 6EI times 2 over P, I guess, yeah. So this will give me PL cube over 3EI. Okay. So we can say that it's the same answer as whatever we've had previously, the same answer right here. Okay. This is when we are using the principle of conservation of energy, external work done is equal to the strain energy. All right. So that's one way to use the various equations that we had earlier. So we have external work done for different scenarios, and also we have internal work done for different scenarios. So we combine them to find our deflection. Okay. So here, this is a direct approach in finding deflections. It's fine, it's good. But then the challenge is that this particular method is only useful, or the principle of work and energy method is only useful for very few problems. All right. So this method, or the method above, uh, is only useful for very few problems. Okay. And again, where the loading becomes a bit more complicated, the principle of the work and energy method will not really work, or will be, I mean, almost near impossible to solve. All right. So based on that, we need to come up with a set of methods that we can use. We have these two methods. So we have one called the virtual the virtual work method, or principle of virtual work. Then we have another method called the Castigliano's method. We will look at this method in this course 255, and then we'll look at the other one in CNG, the 258, which is next semester. All right. So that's something to take note of. So these are the different methods we can use to solve problems using the energy method. So they're all based off the principle of conservation of energy, where external load is equal to internal load, but then we can formulate equations that would help us to solve for problems regardless of what loadings they have. Okay. So let's look at the principle of virtual work. Okay. Or the virtual work method. It doesn't really matter. Okay. It's also called the unit load method. So if you see some books, they might just say unit load method. The unit load method. Okay. This method, I think, was developed by I think Bernoulli. Yeah, developed by Bernoulli, John Bernoulli. I'm sure it's the same guy who did the Bernoulli equation, the Euler-Bernoulli equation. No. Euler is different. He did the Bernoulli equations in the fluid mechanics and some other interesting equations. So it was developed by John Bernoulli in 1717. Yeah. Wow, that's like generations, eons ago, centuries ago. All right. So this again is referred as the unit load method. And this provides a general means of trying to obtain deflections and also displacement, and also what's the name? Slopes. All right. At any specific points on a structure. All right, so this helps us to just put it over here. So it provides a general means of obtaining displacements and slopes for frames, beams, and trusses. Okay. The other options are be limited. Geometric methods, moment area, once you get beam are limited, they can only be used for beams, and even that the loadings have to be simplified. The principle of work and energy also needs us to have simple loadings, and also it can only be used for very few select problems. All right, so they might not be adequate where the loadings are more complex. All right, so we need to come up with other approaches, and one of them is the principle of virtual work, which we'll be looking at shortly. So let's say we have a generalized body. Okay, so something like this, a nice, interesting shape. And then we have all these various loads applied to it. And this is P1, P2, P3, P4. Okay. So what happens is that usually for a shape like this, when you apply these loads, as long as there's a net force, there will be some deformations. All right. So you have your so depending on, maybe in my case, the net force is going towards the northeastern direction. So you have deflections at various points of interest to you, right? Then these are the external loads. So the external loads P1 will also create external displacement delta or external deflections delta. And then inside also we'll have internal what's the name? Internal loads. So let's call the internal loads small letter U. So we also have internal loads, oops, different color. You have internal loads U also acting at various points in the fiber. Okay. So we have all these internal loads, and these internal loadings will also create internal deflections. So the internal deflections delta corresponding to this whole system. All right. So we know that external work done should be equal to the internal work done. All right. So for that to happen, I mean that the summation of all the loads applied with their corresponding deflections should also be equal to the summation of all the internal loads times its corresponding internal displacement. All right. So this is let me just write here. This is work of external. Oops, this doesn't look good. Okay. So work of external loads and then this is equal to work of internal loads. So here, P or all the P's here. So P is external work, or sorry, external load. Delta is external displacement. Then small letter u is equal to the internal load. Then delta d in this form, it's equal to the internal displacement. All right. So this is typically what happens. And we are going to use this information to come up with some equations in there. All right. So now let's again go back to the deformable body, a body that can easily deform when you apply some load to it. So let's say we have this body here. So let me now introduce some supports to the body, and just so that we see what happens. Okay, so there are some supports, as many as we can have. So I think 3 is fair enough. And then we apply again some external loads to this. Okay. Let's say we have P1, P2. It could be as many as we want, P3. Okay. Then this body will undergo some deformation. Let me just do it here. Oops. Nope. Come back. Go back again. Go back. Why are you not going back? Okay. Okay, it is finally. Okay, good. So let me just let me draw. So it deforms because around the supports it won't deform because the supports do not move. So let's say we have a point of interest to us. Let's call this point A. A point of interest to us. Let's call that point A. So at that point, we want to find the deflection at that point. Okay. So we want to find this deflection, sorry. The deflection here is called delta. All right. So definitely, as long as we have this structure in place and we apply this load, and then we take a fiber or an element in the body or in the structure, a small fiber, and then we have an original length, let's say L. Okay. As we apply the external loads, definitely once there's deformation, it means that we'll have a change in the length dl. All right. And this we have this delta. And now let's take this delta and have a case whereby instead of all these different loads, P1, P2, P3, we can create a virtual load. All right. We don't know what load it is, but we can create a virtual load in the sense that when we apply this virtual load at where A is, that virtual load will still give us the same deformation as though we're applying all these 3 different loads. All right. So I take my, let me just redraw this or just copy and paste. Copy, just paste over here. I think this should be okay. Yeah. Okay. So in this case, so here I don't have any of these anymore. I don't have these external loads. But now as where the deflection is, I have a load P acting. So let's call it P prime because it's a virtual. I don't know. It's a virtual load I'm just creating. Whereby this virtual load P prime would end up giving us the same deflection as though we had the real loads P1, P2, and P3. Okay. So as we place the virtual load P prime, that would also create some virtual. So again, I should have deleted, I should have kept this diagram here. Okay. So the presence of the virtual load would create also a virtual internal load. Okay, again. So we have a few things to look at. We have a real displacement delta. So let me just put that over here so that we get our, so delta is a real displacement. Let me say real external displacement. Then the L is a real internal displacement. Okay. Then P prime is a virtual or an imaginary external force or external load. Then U prime, so no, just U. U is also a virtual internal force or load, depending on how you want to look at it. But let's see how we can I don't know. Okay, P prime. Okay. So let's see how we can how we can relate P prime and U. Okay. So P prime and U, if we are to follow the principle of conservation of energy, it's simply P prime times delta. All right. Which should be equal to the summation of the, because this is just here, this space over this one here is just only one fiber, or only one small section of the entire body. So we can have many of these internal loads at different sections across the body or the structure. So we need to sum everything up. So it becomes U times the L. Okay. So the here it looks like the external work done is equal to the internal work done. Okay. But we need to figure out what P prime is. We don't know what P prime is. Our goal is to find delta, the external displacement or the external real displacement. So to do that, we can assume, so let's assume that P prime is equal to 1. Let's say 1 kilonewton. Okay. Or into bracket, a unit load. So it's a unit load, which means that this equation would then reduce to 1 times delta to be equal to, I think a different color would work. So 1 times delta will be equal to summation of U dot dl, which means that delta is equal to summation of U dl. So this here becomes the equation that we can use in finding the deflections, or in this case, the displacements. Okay. And this becomes the virtual work equation for displacements. Okay, so let me just put here, oops. Equation for displacement. And the reason why we call it the unit load method is because we assume that the imaginary load applied here is 1. Okay. We can also relate this entire system to that of the case whereby we, instead of applying forces or axial forces, we can apply moment. All right. So if we have, let's say, an external virtual moment, m prime, then we can also have m prime theta to be equal to summation of the internal load, but this internal load will be the internal moment times the change in the length of the various fibers. Okay. So here, where if our m prime is given as 1 kilonewton meter, then it means that our rotation theta can easily be found using oops, u theta dot dl. So for now, things look a bit off. Let's quickly, we have about 5 minutes. I'll just write something, then we can continue next week. Let's see how we can translate this quickly into trusses. We'll not solve a problem, we'll just continue later. Okay. So in the case, let's look at the method of virtual work for trusses. Okay. So let's say we have a truss. This is a typical truss. And then we have this point B right here. So these are the loads on the truss. And then we have these external loads, P1 and then P2 on the truss. This will end up being the deflected shape of the truss. Okay, with respect to, so we want to find this change here, let's say delta B. Okay, so that's the idea. From our virtual work approach, we know that or we've said our delta is equal to summation of the internal loads times the change in the length. Okay, so that's for trusses. One thing about trusses is that the deformations in trusses, I think we mentioned something like that, deformation in trusses can be due to one external loads. It can also be due to fabrication errors. So when they were trying to weld and bolt, they could have made some mistakes in there. And also due to temperature changes, especially if it's made up of a material that would expand or contract due to temperature changes. All right. So for now, we are looking at here, we are looking at the virtual work method trusses due to external load. So let me just put into brackets here, external load. We'll look at the other methods later. So we know that the internal so let me say that, okay, all the internal load is U. I'll give it a small letter n so that it becomes easy to work with. And then the change in internal length or the internal change in length, we came up with this equation, which was delta earlier, and that was given to us as a, I think earlier we had that delta, which was where was it? Yeah, it was n squared L over 2AE. So that's the internal what's the name? Sorry, yeah. So it was given as NL over AE, which was an internal displacement. So the internal displacement delta L the same as NL over AE, which means that if I want to find delta B, then my delta B would be the summation of small letter n to replace the U, and then my change in length of my internal displacement would be NL over AE. Okay, so we can use this equation. This more or less a generalized equation. So instead of me putting delta B, I can just make it delta. So the displacement at any point on the truss can be formulated using this equation, where the small letter n is the internal virtual or the virtual internal axial force. Okay. And then we have the n, which will be the axial forces in the beam, typical axial forces due to external loads. Okay, so this is internal virtual force caused by, let me put caused by the unit load, which we'll look at next week. Then so this is the big N is the, let's say, the internal real axial force caused by the real loads, external loads. Then L is the length of the member. Length of member. A is the cross-sectional area of a member. Okay. Then E is the Young's modulus. Then delta, so is the external displacement at a point. Which is caused by the real loads. Okay. So we'll leave it here. We'll meet again next week, and then we'll continue from there. All right. Give me some 2 minutes to let's discuss the midsem, and then we can move on. I mean, we can end the class. Okay. So I'll just end the recording here for now, and then thank you.